Okay, so in this meeting, I'd like to again introduce about the confidential computing, particularly on the GPU. Since last time I have present the confidential computing in CPU, and because GPU now is so hot for the AI applications, and we do see that NVIDIA has promote their GPU as confidential computing. So I would like to talk about that. So let me turn to the page 13, okay? So if you remember my previous talk, I mentioned confidential computing, which has become even more relevant than 2 years ago. Today, I will share with you a more detailed version of how it works, what NVIDIA is using confidential computing for, and most importantly, how exactly a path-based confidential computing method is different from others, and why it is more secure. In many applications, computers deal with sensitive data or face certain data regulations, such as health and financial services. And the integrity and the confidentiality of this data can be compromised by unauthorized parties. This is why we need to establish confidential computing, and otherwise known as protection of data in use by performing the computation in a hardware-based trusted execution environment. Okay, so you can see from the page 13, I have illustrated the three protection of the data, which is including the data at the rest, and the data in transit, and the data in use. And the protection of data in use is mainly by the confidential computing. And in the confidential computings, a trusted execution environment is deployed to provide an isolated environment separated from the main operating system, where data can be processed without exposure to the rest of the system. Okay, so please turn to page 14. So to understand how confidential computing works, please look at the left graph. For example, for CPU, in the CPU, the figure of the CPU has a secure and a non-secure zone. Application and OS on regular CPU cannot access the secure zone. However, with the confidential computing, sensitive data from the apps and OS can be stored in the secure zone under individually isolated TEE on the CPU. Now please turn to page 15. And another example of confidential computing is in a graphic processing unit, GPU. GPU has its own hardware rule of trust to enable an isolated TEE for protecting the integrity and the confidentiality of data and the code during the transfer from CPU to GPU, and also processing in the GPU. Based on NVIDIA's H100 datasheet, it shows that NVIDIA used confidential computing for their AI training. As you can see in this view graph, during call and the data transfers from CPU to GPU, the multiple individual TEEs are created through the GPU's hardware root of trust, so that the unauthorized entities are prevented from accessing the AI application data and the code. Therefore, the TEE, trusted execution environment, okay, TEE, needs to have a robust and hardware-based security, which we call it the hardware root of trust, to ensure the following actions. One is to do the device authentications. For example, in this view graph, there are two parts. One is on the top is CPU, and many users use a CPU, and on the bottom is a GPU. Okay, so when the communication begin or the processing begin, then the CPU has to start to communicate with the GPU. So there's first of all is the device authentication need to be done between CPU and the DPU. Okay, so that is when the user and the device are communicating with the GPU, they have to confirm if the firmware and the software of the GPU are secure. And the GPU also needs to authenticate the firmware and the software from OS or apps to check that they have not been tampered with. And the second function is to guarantee the data integrity and the confidentiality between the CPU and the GPU. Okay. A better way to understand this is that the data being transferred will be encrypted and decrypted with encryption key exclusively to the CPU and the GPU, and the data transmit from the CPU and the GPU will be protected. Okay, so this view graph demonstrates the security, confidential computing between the CPU and the GPU. And please turn to the next page. Okay, so we know that in order to set up the in order to set up the confidential computing environments, then we have to know that how to identify. Since we have to set up the trusted execution environment, we have to identify that the trusted execution environment is basically need to be accomplished by the hardware root of trust. So from the page 16, the hardware root of trust in TEE can help protect the integrity and the confidentiality of the data and the codes. It consists of key storage, key generation, and key protections, and the cryptographic engines, all combined for the comprehensive securities. So let's look at this view graph. So our POP-based crypto processor, we call it the POP-CC, can fulfill the role of all functions mentioned above. Our secure OTP, consisting of both our anti-fuse technologies and POP-based technologies, creates secure key storage that hides the key and their whereabouts from the potential attackers. Furthermore, our POP-based TRNG can efficiently generate truly random keys to protect the data and the code. So from this view graph, you can see that for the hardware root of trust, basically consists of two parts. One is the key management, and the one is cryptography. So in the key management also consists of key storage and key generations. And for key storage, we have OTP, and we have also PUF plus OTP to create the secure OTP and also the ultra secure key storages. And for the key generations, and we use the PUF-based TRNG to create the high-speed and high entropy key generations. And I will focus on talking about the key generations and the key storage, since our fundamental technology have achieved a very high skill key storage and the key generations by compared to the conventional methods. So our PUF-based OTP helps the industry migrate to a very high-level security regime by improving the security of key storage and key generations. In the conventional key storage, by using eFuse, and which is basically has not very secure because of the following two reasons. First of all, the burning of because the eFuse is by burning of the fuse. So eFuse require the fuse burning to determine the key, whether it is 1 or 0. Okay, so please refer to the page 17. And you can see the left side. You can see that the eFuse, conventional eFuse, need to, when the data is original 0, and need to be, the fuse need to be burned and become 1. And so when the fuse is burned, it was broken. So, and this method will cause the eFuse can be easy to reverse engineer by looking at which fuse was burned. And there's also the risk of the fuse going back, because the thin piece of metal can sometimes reattach itself, which causes the key to disappear. And the second problem by using eFuse is because eFuse, the size of eFuse is very large, so it cannot overcome the density over 8K bits, and because if the density become larger, and the yield will become lower. So as the technology migrates to more advanced node, eFuse is insufficient to provide the key storage and also other security functions. So with our anti-fuse OTP, we call it NeoFuse, we will not face any issues with reverse engineering, and also we will not face the size limitation and even key disappearing. So we use an electron, because we use electron tunneling method at the transistor level, which can shrink with a process node and cannot be seen under a microscope. Okay, so combining our OTP with our PUF-based technologies makes key storage even more secure. When used with PUF's unique value different from chip to chip, the key's address can be scrambled and stored in a unique randomized location on the secure OTP to make the key storage ultra secure. Okay, so let's turn to the page 18. After I talk about the key storage, the next I'm going to talk about the PUF-based key generation. As for key generation, the conventional true random number generator used for hardware root of trust is not path-based. By comparing path-based true random number generator versus conventional true random number generation in the three categories, path-based is superior for the following three reasons. First of all, the path-based it has higher entropy. Okay, path-based TRNG has much better and much higher entropy because it is derived from the path seeds, which is perfect random sources, make it truly random. Conventional TRNG uses digital circuit to generate random number, which have a low entropy. For example, our entropy is actually about 100 times than the conventional TRNG. And the second advantage of our path-based TRNG is high speed. Another critical feature of TRNG is speed. For path-based TRNG, the speed can generate a high volume of keys, which is about 100 times faster than conventional TRNG. So because the conventional TRNG require a lot of more post-processing, which is slow the speed. And the third advantage is about the power consumption. In our path-based TRNG, we have less power consumption. So the power consumption with the path-based TRNG is also around 100 times lower. Again, this has to do with the post-processing that conventional TRNG requires. So that will lead into more cost and energy use. Okay, so after compared to the advantage of our path-based key generation and the path-based TRNG, now I'd like to make the summaries. So for the confidential computing, in the future, it is a must for GPU and the CPU application because it need to the confidential computing need to provide the integrity and the confidentiality of the data and the code. And as compared to conventional root of trust, eMemory's root of path-based hardware root of trust provides the best quality of unique identity and secure key storage and much higher speed key generation for CPU, GPU, and the DPU to facilitate their confidential computing. And all this, the differences mentioned above why confidential computing architectures are moving away from conventional solutions toward path-based. For example, ARM, is putting our solution as a reference design for its V9 confidential computing, with our developments reaching the most advanced process nodes. We expect increasing adoption of our security solution in the future. And this concludes my remarks. Next, we will enter the Q&A section.